good seeing you.
What's that?
Hi everyone, we are going to get started. If you could take a seat if you find one. Otherwise, feel free to sit on the floor if it's okay with you. Or you can just stand up. Thank you everyone for coming tonight. It's a very crowded room. I knew I had to find a bigger venue to have Ted Dunning and Ellen Friedman tonight. Thank you everyone for coming. My name is Cooccurrence. I'm the Marketing and Partnerships Manager for the Hive. And I'm managing the Hive think tank. Most of you should know about the Hive think tank. We are a group. It's one of the biggest, largest data-driven group in Silicon Valley now. We've reached 4,000 members. Thank you. And our goal is to reach 10,000 members, so we have, please feel free to spread the word, share, tweet. Our hashtag is HiveData if you want to continue the conversation online tonight. So the Hive think tank is a group of practitioners, data scientists, engineers, artists, designers, all focused on big data. We organize events every week almost, 3 to 4 times a month, focused on big data. And we have upcoming events. Those are the 2 upcoming ones. We have one next week in Palo Alto on Kafka with a speaker from LinkedIn. His name is Jay Krebs. And then we will have a panel discussion on Spark on April 9. So we hope to see you there, and we have a very exciting program of events coming up. So make sure to check the meetup group. We'd like to thank our sponsors, especially Wisconsin tonight for hosting us. I don't know if there's anyone from Wisconsin here. Thank you. And Ravi is going to introduce the Hive. He's the founder of the Hive. And thank you again for being here tonight. Thanks. And thank you, Ted and Ellen. Really, thank you.
Thank you, Pastor. So a few of you asked me, the Hive Fund is a funds company, startups in the big data space. And so it's a little different from a traditional fund because we tend to have active involvement in the company, help them from a technology, go-to-market, business, and so on and so forth. The hive itself has operating people, and we have Lance, who's our CTO there, Russell Journey, who some of you heard about a month back, who's our data scientist in residence, who also wrote a book recently called Agile Data Science, who's not here today, and a number of other professionals in different verticals and so forth. So we typically tend to invest in companies at the early stage and then help them, help syndicate financing as they move along. We are looking for entrepreneurs. We just closed a big fund, and so we are looking for entrepreneurs in security, data center management, multi-channel marketing, CRM, finance, and a whole range of verticals. So if you have ideas in this area, we'd love to engage with you. Our companies are hiring, so some of you know one of our companies, E8 Security, which is in the threat security space. They're looking for Hadoop developers, they're looking for Java engineers. For the Hive itself, for 2 different areas, for security and for telecommunications, we're looking for someone with very strong product skills, who's very broad across these areas, who can be a part of the Hive, help us in investing in a bunch of companies. So contact us at jobs@hivedata.com if you're interested. The hashtag for today is Hive Data, and so be part of the conversation. I'm very excited to have Ted and Ellen to be the speakers today. They're good friends of the Hive. Ted is at MapR, has been involved in a variety of projects, Apache Drill, Apache Mahout, Zookeeper, Storm, and has extensively worked on recommendation systems, matching engines, on fraud detection, and in his spare time is playing the guitar and the mandolin. You should have brought it with you today.
No, that would be a bad idea.
That would be competition to your talk. And so Ellen is a very dear friend of ours, and she's also very actively involved in Apache Mahout, is involved in a lot of big data projects, is well known as a writer, has written a number of books, including Practical Machine Learning Innovations and Recommendation, Mahout in Action, and both Ted and Ellen are PhDs. And Ellen has also written a book on with a theme of kind of cartoons and magic. It's called A Rabbit Under the Hat. And maybe she'll say something about it today. Please join me in extending a very warm welcome to Ellen.
Here? You can see I'm so technically able here. Is this, okay. Ooh. So I need to stand by the podium, I can't run around.
I'll run around for you.
You'll run around for me. I feel incredibly short. Well, thank you all for coming. As Ravi said, Ted and I both are big fans of the Hive and the Hive think tank series. And as I'm sure you guys know, if you've been to some of the other presentations, it isn't just that they have better food than most of the other series. They also have some very interesting content and very interesting audience. So it's a thrill to be here tonight, and I thank you very much. I'm just going to give you a tiny short flavor of introduction, and Ted's giving you mainly the talk. We are both authors of this little publication that you're holding, and it's actually a non-technical publication about a very technical topic. So it's a little bit of an experiment to jump into a very technical topic and leave out the technical details and try to get people thinking about the big ideas and the underlying content in a new way. So I'm going to give you a little flavor of that in my introduction and then turn it over for the meatier things to Ted. Oh, this is my contact information. I'll repeat that at the end if you want to get in touch with me. So some of you are new to machine learning. I know from meeting you while we're signing books, a lot of you are working in the area of machine learning already. Let's see a hand of people who don't have direct experience already with machine learning. Is there anybody here who's actually new to the topic? A few of you, not a lot. Well, I also give talks to audiences that are very new to machine learning, and I raise the question, what does machine learning look like? And you might say it looks something like this. And to a lot of people, when they see something like this, what's the first thought that comes into their minds? And the first thought that comes into their minds is, yikes. So to a lot of people who don't have the deep mathematics, the background, the experience with machine learning, the topic, the whole topic, even just the word, is very off-putting. And for this reason, for years, in many ways, machine learning has been thought of as something that's outside of the reach of normal people, outside of the reach even of normal machine or computer scientists or computer programmers, and outside of the reach of many businesses, especially small businesses. And for this reason, when we say outside of the reach, I meant really outside. So for a while in the old days, it was mostly big businesses who were dabbling with machine learning, and they might have one serious data scientist or even a small team of data scientists, but often the team of data scientists was perhaps housed outside in that little hut in the backyard, to keep the scary people away from everybody else. And they're working, odd hours through the night, conjuring up all sorts of very serious thoughts, making all sorts of discoveries. And that was kind of how it was. So it was a separate thing and a special thing. Really now that's changing. And what's happening now is that machine learning and the data scientist team are coming inside the business, and it really isn't just big business. It's becoming an integral part of businesses. Businesses are collecting more and more data. They're realizing that it's important to reap the benefits of that, finding ways to harvest the value from the data that they have, new insights if they want to stay competitive. It's a great tool for getting the work done that are the goals that they already have. So machine learning is really becoming an integral part of the business. But what does that mean? One of the things that it means is that now the machine learning or data scientist team needs to be able to interact with other teams inside the organization. In other words, they have to be willing to share their pizza and beer. So this can present a challenge when people have such different skill sets, in some ways very different language even that they're speaking about these topics, and in a situation that a lot of people still carry that sense that machine learning is something that's special, it's outside the realm of what they look at if they don't have the technical skills to do it themselves. And so we're looking for ways to change that, because it's really important inside these organizations for people to be able to talk between the different teams regardless of their experience. And so I'm beginning to explore ways that people can look at machine learning. Am I cutting in and out here?
Yeah, just pull back a little bit.
Hello? Okay. Looking at machine learning, but being able to think about it if you are the person who has the deep skills and the expertise to be able to actually do it, to be able to think about it in very basic ways and very important ways. In other words, cut to what the key kernel is that matters, partly so that you can communicate with other teams within an organization or outside of the organization. If you're a machine learning service, obviously you need to be able to talk to your clients. Within a large organization, you need to be able to talk to other parts of the business to be able to do your job well. If you're the person who needs the results of machine learning and you don't have those skills, you're not the one who's actually going to execute it yourself, it's also becoming increasingly important not only to have a little basic understanding of the topic so that you can ask for what you want from a team, so that you can understand whether they're delivering what you need, but also so that you can think creatively about it yourself. The thinking should go on all sides of this team, not just for the people who actually have the very expert skills to be able to carry out these projects. This is really changing. For a long time, machine learning has been very much in the realm of being in the research world, and it still is. There are some very, very bright people in a number of academic and non-academic settings who are really pushing forward the frontier of how machine learning can be done in some astounding ways. But I see a separate path coming up now, and what's happening is that machine learning is becoming a very central part of business. So think of this as a kind of a separate flavor. They're both going on in parallel, and they're feeding each other. So the needs of business in the real practical world is setting some challenges for people who do research in machine learning. People doing research are coming up with new methods and techniques, and they have to then begin to look at what point are those ready to move into a kind of practical business setting. And so it's a way of reforming the ideas that come out of research so that they can be practical and productive, taking into account realistic business considerations, working on a timeline that makes sense in business, meeting the goals that make sense in business, doing it from an engineering point of view so that you're looking seriously at the resources involved and always a trade-off between various resources and what the end results are supposed to be. And this is happening now in a very big way, whether it's a large company or even a smaller company that has their own data science team that are building their own projects, whether it's people who are using the many new services, new companies that offer machine learning as a service, or people who are taking advantage of the various open source projects. As Kasia and Robbie said, I have a great interest in the Apache Mahout project. It was one of the first ways that people could do machine learning at scale. A lot of it's a library of machine learning algorithms that are scalable. A lot of it is done on Hadoop-based systems. Some of it's intended to be done not on Hadoop-based systems. I'll just take a tiny moment to mention Mahout in the sense that the project, which just had a new release, the 0.9 version of the project, it's marching toward its full maturity at 1.0. The project is undergoing a lot of changes right now. With the last two releases, it's become much more streamlined. The effort now is focusing in on the parts of it that work the best. Parts that were weaker are being developed out. A less known part of Mahout is the Mahout Map Library, which is an extremely useful tool, both within using Mahout and actually just on its own. It's a very useful tool for people, even if they're not particularly using Mahout. And there are discussions underway in the Mahout community right now about the direction of the project going forward. There are several different extremely exciting new avenues and directions that the project may go. And so I also want to take a moment to invite all of you. I'm an organizer for the Apache Mahout meetup group here in the Bay Area. And Intuit very kindly offered to sponsor our next meetup. That's going to be on the 17th of April. It was announced today, and it's filling up incredibly fast, but there are still some places open. So we'd love to have you join us for that. There'll be a couple of presentations. Ted's doing a presentation. He's a Mahout committer also. Dmitry Lubimov is doing a presentation looking at Spark and the way that Spark might be able to work interactively with Mahout, and also looking at Scala. And there's going to be an open discussion at the end looking at some other changes that are being offered in Mahout and just kind of invite the public in to be part of that conversation. So we'd love for you to join us and at that event on the 17th. Anyway, I bring this up back to my main idea is that machine learning is coming in a very practical way into businesses, even with these open source projects. And so, for example, this is a headline from an article that was published in Wire over a year ago. The little subheader, which I didn't put in my picture here, is that these guys at Overstock.com basically saved millions by doing some machine learning very intelligently, and they used Apache Mahout to do this. Now, the person there on that side, left and right don't work in my head, so that side, you can see he's standing there looking very wise, very knowing. He's also very happy because he's saved millions of dollars, but he's actually not a mathematician. And so I'll use him as my example. It's important to be able to understand machine learning at the level of conceptually what it is, how can it best be used, where is it appropriate, to not be afraid of it, but to embrace it, even for people like myself, who absolutely am not going to be the person who actually goes out and builds the recommender or the project, the anomaly detector myself. I don't have those skills. I would love to have them, I don't. But it's still a very exciting area and very important to think about how it can be used. So I guess my closing thought here is, my goal right now is to find better ways to understand machine learning. I miss doing research myself, so this is my excuse to get in and come up with some new ideas, even though I'm not doing the programming. But also my advice to people who are actively involved in these projects. Machine learning is a way to emulate human decisions and have machines do that for you. It's absolutely necessary when you're working with data at such a huge scale that it's beyond the scope of what humans can actually do directly. But it should not imply to you that it's a completely automated process that doesn't need human insight. It absolutely does. Not only at the end to interpret the results and decide what you want to do with the insights that come from machine learning, but at the beginning. Think before you leap, design your project well. One of the most important steps, may not be the sexiest, but it's probably the most important step in any machine learning project, is to choose the right data. To extract the data well, process it well, make sure you're using data that's going to address the question that you're really after. And another place that human insight comes in is to decide how good is good. What does success look like? It's true in any machine learning project, but it's extremely true when you're doing practical machine learning in a business setting. As I said, there are always trade-offs. You want to figure out what success looks like and what's actually going to give you the benefit that you want, and how much effort goes into getting that tiny extra bit of accuracy. Is it worth it? Well, there's some health care projects where that tiny bit of extra accuracy is worth it. There are a lot of businesses, maybe an online e-commerce business, that huge effort to get that tiny increase in accuracy may not be cost effective. So it really takes human thinking to decide what is the correct target and what does success look like so that you know when you've achieved it. And related to that, very important question is, are you asking the right question when you're designing your project? So I'll just give you the little, do I have time for the little 2-second looking back a couple of years? Can I say the company name? Okay. It's a company up in the city called Shop at Timmy. They were doing interesting online business where they were trying to quickly make recommendations to their customers for sale items, and so that they could make targeted recommendations so that people could find items that are on sale, but items particularly appealing to them. They needed to build a recommender for that. They hired a really, I think, insightful and brilliant and downright handsome scientist. Yes, so they hired Ted Dunning to do this, and I believe he used some algorithms from Mahout, yes, to do it. And they built a really kick-ass recommender, and it was just targeted, and it was just excellent. But it wasn't, the business wasn't getting the pickup from the recommendation that they expected to get.
Excuse me, it didn't work for shit.
So the bizarre thing is that the recommender worked. the recommender worked very, very well, but it didn't produce the desired result. It gets back to, in the practical world, maybe it's a good recommender, but it's not doing anything for the business, you know, not very useful. And so Ted sat down with them, and they all put their heads together, and they figured out that they had started off basically by asking the wrong question. And so it was a timing issue. They were going in, looking at what was available as sale items, having a very sophisticated way to target that, to get the correct, you know, look at preferences, get the correct item recommended for the right person. All of that part was working, but the timing was wrong. They were coming in too late. It turns out it's a little bit of the old-fashioned image of a department store putting on a giant 24-hour sale, and in the first 15 minutes, a huge crowd rushes in and crush each other and try to get all the good items. And the person who waltzes in 4 or 5 hours later, you can then say to them, I can figure out from your preferences what's the best item to offer you, but it's the best item from a bunch of crud that's left over after everybody took the good stuff. And so this was literally happening in this business. They made a slight adjustment, started, changed it so that the recommender was looking for items within a certain tiny time frame of when those sale items became available, and suddenly bing, and it worked like crazy, and the business got a huge pickup. So it's a very easy to understand, but it wasn't obvious from the beginning example that it really does matter to have ask the right question, use the right data, have human insight both in the planning going in and looking at the result. It's not just a matter of whether you pick the right algorithm. So I think I don't have time for the rest of my Yeah, I'm going to leave you with that thought. There are some extremely important ways that you can simplify the way you look at this material, even if you're the expert doing it. And I will leave you with the challenge that when you do that, it not only makes it easier for you to talk to the less technical people with whom you interact, but it will surprise you by looking at the very basic concepts, getting away from the details for a little bit. It absolutely frees up your thinking to come up with really great new ideas, real discovery, real innovation, real creativity, and in many cases simplifications. And simplifications often, if they're the right simplifications, can be the key to making these projects hugely successful. So thanks a lot. I'm going to turn it over to Ted.
I want to slightly correct that story. I didn't come up with that idea. I did what they asked me to do, as all good consultants do, and I didn't come up with the right answer because I accepted the question as given. It was the wrong question. One of the lowly guys there, who was kind of new out of college, he figured out what the right question was, and then the problem was easy. So you hire the high-powered guy, and if you ask the wrong question, if you don't step back, like she says, you get the wrong answer because you asked the wrong question. So I'm going to talk a little bit about how we can do a better job of that. And this is my break for freedom. I have 6 inches more freedom now, but I still have to hold still. So anyway, what I'm going to talk about is introduction to Mahout. But in particular, notice the red, see, matches. That means I work for MapR. But in particular, I want to talk about Mahout's recommenders tonight, because it's one of the most approachable parts of Mahout. I'm going to talk about what recommendation is, what makes it different from some other machine learning type problems. I'm going to talk a little bit about what multimodal recommendation is. It's not much covered in this little book, but it's a really important idea because it lets you start thinking about what the right problem is, what the right data is. It lets you be flexible and agile. And I'm going to talk about how you can build it using things you find around the house on a weekend, sort of thing. Yeah, and I'll give a detailed breakdown of a system. I may have to summarize just a little bit, but we'll get on that. So here's a quick 5 minutes of background. Then we're going to do, I want a pony. Everybody wants a pony? Raise your hand. Okay, everybody who lies, raise your other hand. Yeah, you should have told us you wanted a pony. Everybody wants a pony. Come on, don't give me this stuff. Unless you don't know what a pony is. I mean, that's the only way a little kid did not want a pony when they were little, I think. I was just telling a story recently about how I came very close. We lived on the East Coast for a little while, and I came that close to spending all my allowance surprising my parents by buying a pony. Very, very lucky I didn't do that. So anyway, here's the background. We're going to talk about machine learning. It isn't this scary stuff, though. It actually is everywhere. You see these systems in all kinds of situations. You see the classic sort of recommendations. Movies, books, and so on. But here's a recommender most people don't think of. Come on, not to me. There we go. This is Google Maps. It's a recommendation engine. I searched for Piatti's. It's a restaurant. How would you know the word Piatti's is restaurant? It doesn't even have the word restaurant in its description there. And so what does it show on the map? Well, it shows Safeway, another food place. It shows the ATM. It does show Oracle. Well, that's kind of prominent. But it shows Pedro's Restaurant Cantina, Parcel 104, which is a restaurant, The Demon, which is a bar, IHOP, which some people claim is a restaurant, and Burke's, which is a restaurant. So it showed restaurants. Now, here's the same neighborhood pretty much, and I searched for MapR. So it shows Software Solutions, ITRI Electronics Research, these guys who rent offices to advanced technology people. At Lona, I don't know what they do, but it says technologies, medical device guys, photoelectric stuff, patent attorneys. So all techie stuff. What's missing here is the restaurant. It's right there, Barrels. It's in our building. It's not there because they know that I asked for a high-tech business. So they're showing me other ones that other people might want to see. It's a recommendation engine. Doesn't look like it. It's not saying you people who bought MapR, well, anybody who really wants to buy it, you can do so, maybe. But people who bought MapR definitely didn't buy those other things. A, nobody's ever bought it, and B, those other things haven't been bought either. It's not doing that sort of thing. It's watching how people behave relative to maps, and it's figuring out how I'm likely to behave, and showing me related things that I'm likely to be interested in. If I were to click on the light rail station over here, suddenly it would show transit map. Again, a recommendation. So we find these things everywhere. They are ubiquitous organizing principles and devices for websites anymore. I want a pony. This is how it works. So, the basic idea is we want to look at the behavior of lots of people and figure out what the behavior of a single person is going to be. The problem, the real hard problem here is that we don't have enough history from any given person to figure out what that person is going to do. We can't build a model of a single person versus all of the things in the universe. And we can't really build a model of the single thing because then we would have to evolve and evaluate hundreds of millions of models. So what we have to do is kind of interpolate. We look at what everybody does, look for patterns across that, and then find out how you might match some of those patterns and presume that we can extend those patterns to other people, to you even. So, here's a very simple example. Alice got an apple and a puppy. Charles got a bicycle. Easy enough. Bob shows up and he's got an apple. What are we going to offer him? What do you think he'd want? Well, the numbers are kind of small. 3 instead of 3 million. But the only person who ever had an apple in the history of the universe here got a puppy. Hey, let's offer him a puppy. There's a reasonable thing. So what else? I mean, this isn't so bad. This is mathematics. Don't kid yourself. It's mathematics. It's going to be advanced mathematics before we're done with it, but it's not scary mathematics. It just makes sense. I mean, that's the whole definition of math. So you got the idea. That's the basic idea. Look at what other people have done. But here's the problem. Notice everybody's got a pony. Like I said, everybody wants a pony. So Amelia shows up and she's got a pony. What does that mean that we should recommend for her? And as I said earlier in the colorful sort of way, doesn't mean shit. Doesn't mean anything, really, other than she's just like everybody. So maybe we offer her the most common thing, apples and puppies. But that's just because we know she exists. The pony has told us nothing. So we see the two problems. One is to find interesting co-occurrences, that's the apple and puppy, and discard uninteresting ones. That's the pony and everything. That's uninteresting. And so we're going to have to solve that. Very popular items, like the pony, co-occur with everything. Widespread co-occurrence is not interesting. We want anomalous co-occurrence, something that's relatively rare, and yet it commonly co-occurs with some other thing. That's going to give us hints about what the world means. Now, there's a very simple test. It's called the log likelihood ratio test. It allows us to look at when things occur together and when they occur apart, and look at those numbers and put a measure on how interesting that co-occurrence is. Here's our history. This is our log file from earlier. Now, it's normally going to look a little bit more like this and a little bit less pictorial, but you get the idea. So we're going to turn that into a history matrix. Each row contains the history for a single user. Each column contains the history for each item. Now we can see that apple and puppy co-occurred with one person. Apple occurred without puppy in one person. Puppy never occurred without an apple, and one person had no apple, no puppy. So we do co-occurrence counting to encode that for all of the items at the same time. We can do, therefore, kind of a wholesale mathematical operation. And then we can analyze this to find out which of these are anomalously common by breaking it down into pair by pair instances. Remember how those apple and puppy, that's Alice. Apple, not puppy yet, is Bob. And Charles is the one not apple, not puppy person. Now, what we want is a number on this that says big when it's exciting and little when it's not. Here's 4 examples. It's really 3 of them because 2 of them are linearly identical. The first one, B occurs 1% of the time when A is present, and it occurs about 1% of the time when A is not present. 1.3% actually, and 1%. It doesn't matter if A is present. B doesn't care. So that's not interesting. The one on the upper right, A and B only ever occur together, never apart. But it's also uninteresting because we have very little data. Lower left, they only ever occur together and they're both relatively rare. This is the beginning of interesting. Hey, at least it's a coincidence of rare things. If you see 2 rare things right next to each other, you kind of go, I'll keep an eye. But it doesn't lead you to change your life. Now, the one in the lower right, we see A and B together 10 times out of 100,000 events, and we never see them apart. At that point, you go, they are connected. There is no way they are not. You just come to that sort of conclusion. And the log likelihood ratio comes up with these numbers. Now, 5 standard deviations, these are roughly in units of standard deviation. 5 standard deviations is enough to declare a new subatomic particle. We missed. Sad. So we don't have a Higgs particle in the lower left, but we do in the lower right. That's 14.5 standard deviations. That's astronomically rare. 4.5 occurs like 1 out of every 50,000 things. And when we have 100 million things, there are going to be a lot of things that have this kind of co-occurrence. Yeah, it's probably still worth putting in the list just in case it's good. When this occurs, it's going to be like 1 in 100 million sort of case. That's rare, that's astonishing. 1.95, 1 out of 20 sort of case, who cares? Just absolutely, who cares? Because 1 out of 20 of 10 million is 500,000 things, like you and your 500,000 best friends. But if any one of them talks to me, I'll tell them I saw you. No, it's not gonna happen. But this one, this is your identical twin on a planet that kills all identical twins at birth, that sort of thing. This is extraordinary. That's kind of unusual. That's nothing. And this is emphatically nothing. We have enough data to say it's nothing. Here, we just don't have enough data. It could eventually turn into this, but it's not interesting enough to keep an eye on. So, we now got it. We got all the pieces ready. So we're going to take the co-occurrence matrix, and we're going to reduce it by using this thing, and we're going to just keep the top 100 most interesting co-occurrences per row. We call these indicators. Apple is an indicator for puppy. Now, somewhat paradoxically, puppy is an indicator for apple. We're ignoring time. Presumably, she got the apple before she got the puppy, because that's the way we wrote it. But often it's good to ignore time. Often it's good to be reversible. If you did not ignore time, then you would never recommend a new razor handle to somebody who just bought razor blades, but you would always recommend razor blades. Hey, they might have lost the handle. You might mention where it is. If somebody watches episode 3, you would never recommend episode 2 or 1. Hey, they might have come in the middle. They really might like that link back to the beginning. So ignoring time is often a useful thing. It's a pragmatic sort of decision. But once we have these indicators, we're ready to roll. What we can do, and this is the cool and easy part about it. This is the part where you do have these things laying around, at least your business probably. You can take a single row of that indicator matrix, and you can put it in as a field. This is a document here, a fielded document of the sort that you would stick into a search engine. So a search engine has fields like a title, a description, things like that, maybe a price, maybe a URL that links to the image. And we've just added a new field called indicator. And the indicator contains things that were the non-zero row elements in that row. So that when we search with behavior, this apple, consumption of an apple, getting an apple, is behavior that we observed. When we search with that behavior in the indicator field, we get puppy. There's no mechanism left. Once we have the indicators, we can build an index like this, or just augment an index we already have. And Shazam, we've got a recommendation engine. Too good to be true, almost. But very, very easy to do. All right, keep doing that. So that one row becomes the indicator field and everything, and that's how we built this thing. Here's a picture of it. What we've done here is we took music listening logs. Now they were statistically generated, they were synthetic, they're kind of garbagey, but they make the point. And what we're doing here, this is a commercial version of Solar, which is based on Apache Lucene, Apache Solar. And it's searching here for indicator artist 2122. That's Fats Domino. Or indicator artist 303, that's the Beatles. In case you can't read it, here we go. And the result is Chuck Berry. So early rock and classic rock, and you get Chuck Berry, absolutely epitome of early rock. Nobody's heard of these people, but this is all plausible, just trust me. The other example I have is Duke Ellington and Udi Bowman. How many people here know what Udi Bowman's music sounds like? See, that would have been worse. But the interesting thing here is that it is just an ordinary text retrieval that we're doing, and we're getting recommendations out of it. We're searching this indicator artist field. And we're doing ordinary text retrieval. There's no thing added here. This website comes as part of the system. It's very easy to integrate into your own website, and it's easy to build navigation into this. Here's a more elaborate example where we might have recommendations for vendors or something like that, coupons. And you've got all the sort of things that you might need to show the user if they want the coupon. And you can add indicators for other merchants they've purchased from, other industries that they purchased from, offer text that was in offers that they had redeemed that becomes indicators for this offer. And the query becomes current location. That matches location using the normal search engine technology. And then all of these recent behaviors, this one is here just to say, hey, give me whatever's good locally, the popular things as a backup for a cold start sort of thing. And we have this very, very nuanced recommendation engine now. We can include or exclude any one of these pieces of the query for specialized kinds of recommendations. So we actually have something like, what do we got? 1, 2, 3, 4, 5 indicator sort of fields. So we have 32 recommendation engines in one. We can tune, we can test to see which combinations really work well for us. And it's really easy. There's one big job to find all the indicators. The indicators change slowly. And then there's the real-time part, which is the search, like this. The original data is augmented by indicators. The recommendation query does it. Now, some of these behaviors that we're searching with indicators are different from the behaviors we want to stimulate. That's a thing called cross-occurrence. So instead of co-occurrence, we said apple co-occurs with puppy. You can actually have one kind of thing that occurs with a different kind of thing. This is a bipartite relationship. And this is a great example of rolling it back. This is, frankly, it's another mistake that I made. I was presenting this basic idea of recommendation to a team and a company I was at. And I said, look, you can do this as matrix multiplication. That co-occurrence computation is matrix multiplication. You can do it as a self-join. You can do it all these ways. A transpose A or B transpose B, where A and B are two different kinds of history matrix, could be that. And I said, of course you could do B transpose A, but it makes no sense because we're not doing that. But I had broken it back down to the basic ideas enough that one of the guys on the team says, why not? I said, because it's stupid. I was talking about myself at that point. I didn't realize it. It was stupid not to think about that, not to go back and look at the shape of the data, look at how it worked. This is not that complicated if you bring it down to these very simple shapes of the computation. And in fact, the B transpose A idea turns out to be really, really cool. Here's an example. We made a test case of 1 million videos. The problem with the videos is that searching the content of the videos is very hard, because it's video. It doesn't, it just doesn't come with nice indexable things. And this was years ago, so doing magical googly things like understanding the videos was just out of scope. We had a week to do this. And it comes with text. The text looks attractive, and it's absolute garbage. So the two situations that happen, one is somebody puts the latest hot movie onto your website, going to get you in trouble if you don't find it soon, but they label it as my grandmother gardening with the cat. And then on their website, they put a pointer, says, this says my grandmother gardening with the cat, but in fact it's Iron Man. Go here to see a pirated video. And we're sitting there going, whoa, grandmother video. We got a lot of grandmother videos. And they're really popular. And we're going, what's going on? Well, we have no idea there. But the people who search for Iron Man eventually find this website, come back and watch that video. And so the query behavior, matrix A, and the video behavior, matrix B, could be combined. But we can't do a text search to find that thing. And the other thing happens too. People label it Iron Man episode 3 or whatever it is up to now. And it is actually their grandmother gardening, and they're going, ha ha, trolled you. Thanks guys, we just made everything garbagey. So what we want to do is put in a query like Paco de Lucia. He's a flamenco guitarist who moved into jazz, invented a thing called New Flamenco. An amazing guy, just died sadly. And if you do text search, because there was no Paco de Lucia videos in this test set, but there were 400 episodes of Spanish daytime television, Hombres de Paco. And from the text point of view, 2 out of 3 words. 2 out of 3 words matched. It's gotta be right, right? No, it's grandmother gardening sort of thing. From the standpoint of somebody who wants to see Paco de Lucia, this other stuff is bad, really bad. But the recommendation-based search found flamenco guitars and dancers, Van Halen doing a classical guitar riff. Here's the pictures. I mean, you can see that's not much about flamenco guitar. It's about stuff. I don't even know what the top picture is. I don't want to know. Yeah. But if you do care, it's season 4, episode 10. So there you go. Here's the recommendation results. The top one is Concierto Ciudad de las Indias. That's a classical Spanish guitar piece. Second one is CUD. Hey, what's that? I don't know. But they're dancing the bulería, which is a flamenco dance. So it looks like somebody engineered this data so that they said, CUD, that's a flamenco dance troupe. Bulería is a flamenco dance. Flamenco dance is done to the accompaniment of flamenco guitar. Flamenco guitar is kind of Spanish guitar music based on the Jewish communities in eastern Spain. And classical guitar is this, and this guy did this kind of thing, and he invented that kind of thing. And then here's these deep connections. It looks like somebody engineered all that here. It really does. And in fact, somebody did engineer all that knowledge for us. It was our users. They typed in Paco de Lucia and eventually watched this dance group, some of them. Enough of them that we saw the pattern which connected his name to flamenco dance, and that flamenco dance in particular. Here's more of Vincito Amigos stuff. Here's Van Halen doing a little bit of classical guitar. It's a 20-second video. Nailed it. It's so cool that that pops up as a hit here. And then here's a guy in the dorm room doing what he thinks of as freestyle flamenco, which most of us would not use that adjective. But it is connected to that word. Here's another example. We built this. It was hilarious. We put a logo up on the website. The first 20 people who came in got an under construction sign. After that, we put on the page, linked to by the little logo, the recommendations for all the people who clicked on the logo. So by definition, the stuff that was on the page that was found by the people who clicked on the logo was the stuff that the people who clicked on the logo wanted to see. It's cross-recommendation. We're cross-recommending from clicking on the logo to watching videos. And the logo we tried first was fast cars. And literally about 5 minutes later, there was enough data that that page was full of, all the teenage boys, what they wanted to see was fast cars and girls in bikinis. And that's what was on that page. It was self-fulfilling. It was completely circular reasoning. It was a trivial exercise because the whole website was organized by this search engine. So we just had to say, the search here is people who click on this logo. Recommend for you. Very easy. All very clever mathematics, but very easy to implement. But we can do better. This was one kind of behavior to another, or the same kind of behavior to the same kind of behavior. We can do it all at once. So here's the idea. This is the matrix form of all the stuff we've been talking about. The idea is A is the history matrix, and we multiply it times a user's history. It turns that into a list of users who are similar. A transpose then turns that back into a list of items. This is a classic recommender. People who watch this also watch that. The clever thing to do is we do the indicators that in the parentheses, do that offline because it takes hours, and the stuff outside the parentheses is the search engine. It's doing a matrix vector multiplication. That's what search engines do. So that's the item-centric recommendation that we're talking about. But we could have done B transpose A. Yeah. But we could do even better. We could take the history of things that we were talking about and break it into more than one matrix. The history of what people have done with type 1 and the history of what they've done with type 2. It's an adjoint matrix. The rows are all the same, but there are more columns now for different kinds of behavior. And even different kinds of behavior with the same items. Did you click on the video? Did you watch it for 30 seconds? Did you send it to your mother? Different behaviors, they mean different things. And they mean different things for different kinds of items. So looking at something, if it's very expensive, is quite significant about your desire for it. But purchasing something that's very cheap might be what really is the interesting behavior. So then we can do the whole recommendation thing on that adjoint matrix. It gets bigger. But this bottom thing is cool. That's straight recommendation. That's cross recommendation on a composite history. We can do them at the same time. This means that we can build multiple indicator fields into that same search engine and do the queries all at the same time, all of it in real time, just as easily as if we just done one. This is cool. It looks fancy. That's why I put it up there, you know that. But it's really easy. And the question of how easy is it, I gave this, basically this talk, not quite as pretty, not with the pictures, to a group who was visiting us, doing a workshop at Nap Park. And on Friday they left. That's when I presented this ideas. They left, they flew home to New York. I flew out there and visited them on Monday morning, and they had a prototype built. They went from 0 to I can't find it, I have a phone around here somewhere, to a mobile application in users' hands. This is a bank. The moment is past. But the idea is that they went from 0. They were people just out of school, basically no big data experience, just smart guys, smart ladies too. One of them had a French degree, but she was really smart and mathematically inclined. And in 4 months, they went from nothing and very little experience to a product in customers' hands at a bank, which is truly the amazing part of the story. Smart people can do amazing things, but not usually at banks, because that's a very cautious environment. So, but literally, over the weekend, one of those guys had built a prototype of this. It's that quick and that easy, and they were able to field an entire recommendation system with multimodal, multiple kinds of behavior. Now, there's one cool thing I wanted to add here. This is, it's how you make your recommendation engine worse in order to make it better. These systems, if you think about it, critically depend on what data you give them. If you give them a broad education, they can make very, very exciting and cool recommendations. If you only give them a very narrow education, they will give you a very narrow view of the world. So if all of your user histories are based on linkage to episode 2 sort of things, you give them no search, you give them no way to discover things, that's the training data you'll give these, and these recommendation engines will only ever give you that kind of data back. You need to let them explore a little bit. They have to explore in order to grow. But the worst thing is here is they choose their own training data. Because the stuff the recommendation engine says on day 1 becomes training data on night 2. And then that is the recommendations on day 2. And if the data is just what was recommended, the thing will never learn anything new. It will never even learn something that's at the edge of what it knows might be wonderful. So the trick here is we jiggle the results. We rearrange them so the top things stay near the top, but the deep things can be dredged up and become part of the training examples. And it's guaranteed to make performance worse right now or in any kind of offline recommendation. But what it does is it gives the system a broader view, lets it explore more, lets it find exciting new connections. And so it makes recommendations better later. It's an investment you make. And among the people I've recommended and they've tried it, there's almost a perfect record of people coming back and saying, we tried dozens of things, and this is the one thing that made more difference than anything else. Because the data you put in is what determines the quality of what comes out. We've heard that phrase before. But it makes 200 or 300% difference, whereas changing algorithms makes 2 or 3% difference. It's a massive difference. This can make a huge difference. Other tweaks make very small differences. That's what they say, over and over. It's very easy to build. You build a real-time recommender, you keep logs, you do overnight training. And here's why it works. If you look at horizontal axis of rank, how deep are the recommendation results, and you look at vertical axis as click-through rate, what happens? It decreases. People don't tend to read down the page very well. They look at the top few and they get bored. But at the end of the first page, they don't click to the second page. They don't even much scroll to the bottom of the page. And if you could just screw it up so that these results appeared on the first page sometimes, you could learn which of those were really, really, really good. Paradoxically, if you have an interesting recommendation page, people will come back to that page, even if they won't click to the second page. So you compensate for them. I mean, they are your users. They dominate everything. So it's a very simple thing you do. You build a synthetic score. It's the rank, actually it's the log of the rank, plus Gaussian noise. The size of the Gaussian noise determines how much mixing happens. Here's what the mixing looks like. Each row is a list of numbers that's 300 long, and I'm showing you 10 of them. Yes, 10. I'm showing you the top 10 after dithering. And so you can see for sigma, or epsilon is 2, that, what is it, 33 and 44 and 33 again and 22 appear on this first page. With more mixing, we would see even deeper results. Without the mixing, everything that would appear on here would be 1 through 10. We wouldn't learn about deeper things. But notice also that the top item is always in the top 3 places. So it's always near the top. We haven't heard that much. So that's dithering. Dithering plus search as recommendations makes everything cool. Oh yeah. Remember I said, here's how you do it. Well, you take your history, you run it through the row similarity job of Mahout, put it into Solr or Elasticsearch, whatever your handy search engine is. I suggest doing it on MapBar. It's because I wear a red hat and they give me free red hats. There may be other reasons too. I think it's really cool actually. And then to deliver it, bam, there's your search engine. There's a web tier. That's all it is. Co-occurrence analysis and the search engine. That's how you build these. Thank you. And
So we can take a few questions to kind of Ellen, for both.
you guys look tired. Probably talked too long. Here's a question, Santosh.
Yeah, it's a, these engines, when they start making life decisions, we thought about that.
So he asks if these agents start making life decisions.
Decisions.
I think you mean like important decisions.
Yeah, you know, like important decisions could be in recruiting, could be in the layoff, you know, like that side, or it could be in the health sector, or maybe defense, I don't know. But when these teams starts making those decisions, and you are in the tryout phase, you know, like, so, you know, there's an ethics side of these things that starts coming.
So he asks about the ethical questions here. We're putting random numbers on this. Now you could dial that up or down. You could put more or less random numbers. But what do you do when it really, really matters? And to my mind, what you do there is you provide multiple ways to find results. But one of the key problems that we face today is this information overload. There is so much garbage information around that there has to be some way to bring the good information up to where we have a chance of observing it. If we don't have a chance of observing it, if we just look at things without any tools at all, then we'll never find the important things, and it will be very, very bad. But this is not the only tool that we should use. We should use a real search engine, because the metadata may be correct. We should see all of the examples if we can afford the time to do so. And we should use this. We should use most popular. We should talk to people if we're making important decisions. But these kinds of systems can find information that people need to find or want to find much better than systems without good recommendations.
Oh, no, I agree with that, where I'm just, like struggling a little bit to kind of think it through, is that right now for those important decisions, we depend as a society on the humans.
Mhm.
And humans, for some reason, they also make bad decisions, it's not that they don't. But those decisions are more socially acceptable and we trust those decisions.
I'm going to summarize real quick so they don't just sit there wondering what you're saying. He says that for now, we depend on people to make their decisions on these important issues, and that it's kind of okay when people make their decisions as opposed to machines, I think, yeah?
Yeah. And so if the people we start taking out of those decisions making and more machine does, don't know.
So what happens when machines start making decisions? Well, machines already make those decisions. And in most cases where it's really critical, you have to measure whether they make the decisions better than a human or not. And if they make the decision incomparably better than a human does, then the machine should make the decision. If it's kind of 50-50, you should use both. And you should make the machine explain itself, you should make the human explain themselves. But for instance, who here wants to wait and ask a lawyer whether the airbag should go off? It's an inhuman decision, but it's a little classifier sitting in there. Is this a noise? Is it really a crash, or is it not? And that was one of the most difficult things about airbags originally, is to build a system that would decide when they would go off. And now we have no problems with this because they do much better than we possibly could, and they save many, many lives. Now, just as important to me, I'm sure, these video recommendation systems really, really work.
But you must have heard recently that on Toyota Prius software bug created like 2 million recalls of the vehicles and all that, right? So
Software bugs are horrendous, and we need to not trust software too much. We need to test it, and we need to decide when it's working. Absolutely.
Yeah.
Yeah. Sure, back there.
This is about deterring. You had, in your second bullet, you said it's guaranteed to deteriorate offline performance. Can you elaborate on that? What do you mean?
The man has studied mathematics, I think. He said, I guarantee that it will make performance worse. That was the talking about the dithering. Say what?
No, I just want to understand it. I'm not
Yeah.
asking the
So,
math.
coming from a little bit of a mathematical background, not being a mathematician, the words guaranteed to make things worse are tantamount to fighting words. It's a big claim. But the fact is, it's really a simple argument. The order that things are in from the raw engine is our best known order. And any randomization from that must, on average, be worse. It's certainly not, on average, going to be better all the time. And so just the fact that it's randomized, it's going to be worse. But that is good in this case. We have an explore, exploit trade-off that we have to make. We have to explore enough to get good training data and still exploit. But that guaranteed, if we do only offline evaluations, we will always reject dithering because it always appears to make things worse, even though it is enormously better for social reasons, that it makes the overall system better. Yeah, way in the back.
Is dithering substantially better than correcting for that function? I mean, presumably there's going to be some neat functional form.
So he asks whether we should correct for the fall off. Well, the fall off in click-through rate is actually correct in some sense, that the top items should be better than items ranked lower, if our ranking is any good at all.
Right, but
So,
if for a particular video you have a significant deviation from the predicted click-through rate,
yeah, and what you're suggesting, where we look at where something has appeared in results and try to estimate whether it is appearing too low in results, that's fine and good, because that tells us in some sense whether a video should have a generalized boost. But it tells us across all queries that it might have appeared in. And so it, in some sense, isn't telling us much that we don't already know. Whereas, since we're looking at the entire history of what the person has done, and we're bringing in extra things from the results list, we are going from query 20 minutes ago or 10 days ago to video right now, not just in the context of the current search. We're finding things we didn't know. As the people restate their queries, they're traveling from their original point to a new point, and we're learning across that journey. And so just correcting for expected click-through rate at a point in a query doesn't actually work that well because it's too tight a feedback loop. It's not broad enough. And it also doesn't learn what the important connections are. What is it that is better about this? What context should we show it highly in? And what contexts should we not show it at all? That's what it fails to learn in those cases. I've tried both. And the fact is that this cross-recommendation learns the content connections from query to content in a much deeper way than just, hey, I ranked this too low, therefore I'll goose it up a little bit.
I guess I don't see why you do both.
You can do both, but the one
Works much better.
just dominates the other, so that the other is just noise in the game. Yeah.
So, in one of the slides, you have 2x2 matrix where you had numbers put in with A and B, and you mentioned that one of the probabilities is 0.9,
Ooh,
the other
yeah.
one is 1.45 and others.
So he talks about the 2x2 matrices, yeah.
And key thing that you mentioned there is that enough data. So, what is enough data points? I mean,
Ooh.
10,000,
Ooh, I hope you all heard that come out of his mouth, because it's such a wonderful question. What is enough data? How big is data? How high is high? How big is enough? Well, it's really hard to say, because it varies dramatically by context. But the wonderful thing about that particular test is that there are three possible answers. Not enough data, no connection, good connection. Those are the three possible answers. And it can only give us two. But what it does is it pushes the two that we don't want to know about into the same bucket. So not enough data and no connection, it puts into the low numbers. And strong connection, or not, well, interesting connection, may or may not be strong. It's just we have enough data to really say what it is, gets the high score. And then we'll weight it as to whether or not it's a strong connection somewhere else. And so it lets us avoid the question of what is enough data. Now, practically speaking, based on experience, enough data in music is if you play 5 songs, 10 songs, then I will be able to recommend fairly accurately to you, enough to give you an hour of fun. And during that hour, you'll click on skip sometimes, and I will learn from that. How long you listen to a song is a very complex indicator of what you like or not. If you listen to 5 or 6 seconds, you probably like it a fair bit. If you listen to a quarter second, you hate it. If you listen to 30 seconds, you really don't like it. If you listen to the whole thing, you're a little bit neutral to positive. But from those skipping behaviors, I can learn a lot more about you, especially if I have a lot of dithering going. So how much is enough? 5?
But the question is, when you arrive at that decision point for that 5, after 5 songs, you are able to recommend the other songs based on that. The question is, how did you come to that initial recommendation list? I mean, is it 10,000 users, is it 5,000 users?
How did we come to the original recommendation?
Right.
So I've never done this much with small user bases. Typically, the number of users involved have been from 1 million to 100 million users, and from a few tens of millions of observations to hundreds of billions. Now, this sparsification style, this LLR-based, indicator-based stuff, tends to fail when you get too few observations. If you get less than sort of millions of observations, it doesn't work well because there aren't enough connections to be made. There's not enough co-occurrence to be made, unless you have very few items. But when you do have lots of data, and really there's an awful lot of data to be had in most cases, then it works quite well. When you have smaller data, then there are alternative techniques which are much more complex mathematically. as is typical. Small data is much harder to analyze than large data. But among the people I signed books for tonight, I'd say that 80% of the people have pretty dang large data compared to the limits here. And so I would almost always recommend this type of technique. There are three kinds generally I'd recommend, but this is the most common by far for recommending it. I'm recommending of 3 items, yeah. Right? I just caught myself. Yeah.
How you will separate the bad data from?
How do we separate bad data from
for
good
example,
data?
you have Sally she bought the puppy and the apple, but maybe she bought the apple because she was with the boyfriend who likes apples.
Yeah, so there's 2 questions here, really. One is, how do we separate good data from bad data? And the other question is, how do we separate socially complicated reasons for buying something from simple reasons? So I'm going to answer the second question first. And the second question is, I don't care. If there's a strong pattern, I'll go with it. It may be that all 30-year-old males live with their mother and buy her presents every week. If so, I'm happy. I will recommend presents for their mother if they're 30-year-old males. I mean, if that's the way the world is, I will be. If a lot of women buy apples for their boyfriends, then that's fine. But the noisy situations where there's unusual stuff, like the guy's boyfriend buys an apple for her mother or something, but really complicated, and it turns out that it was really her brother-in-law that needed the apple. It's like,
Yeah, it's good for you, but it's not good for Sally because she will receive recommendations for the apple that she don't actually, she's not interested in apples.
well, after she breaks up with him, probably not.
For example, I watched The House of Cards and I saw the bourbon
Yeah.
Frank Underwood drinks, and I was curious how much it cost on Amazon, and I just typed that kind of bourbon. And next time when I visit Amazon, I'm receiving a lot of bourbons recommendations.
Now, let me give you a much stronger example. I mean, you might like bourbon. You should have tried it. But no, here's a much stronger example. What kind of music do you recommend the first week of January? Christmas music? Everybody seems to like it? Well, maybe not anymore. You should stop. And those sorts of things, the system will make egregious mistakes. It will recommend Christmas music until Christmas falls out of fashion. But we kept 1.5 years of data, so it always had Christmas. You know, it's always saying, maybe you'd like some Christmas music. Because on average over the year, it's not such a bad recommendation. And so you may have to layer on some additional logic, like don't dare do that. We're just turning that stuff off. That you have adjustments to make. And seasonality, if you don't have seasonality built into the model with explicit variables for it to use, can be very hard for the system to understand why people have quit listening to that. You did have something to add there.
Well, and, you know, I shouldn't jump in, but I'm going to, because you really hit a nerve,
I
because this
jumped in.
bothers me. It was a great question. But isn't that part of the issue that if your recommendation system is using a method of saying, I've watched your pattern or Sally's pattern of what she gets, and so I'm going to recommend items that have characteristics similar to that. So I know I bought a red book, so I must like red, so I'll give me a red shirt or whatever. So it's trying to look at the characteristics of items based on a short history of me as an individual. You come up with really bad solutions. But if you use the kind of recommendation that Ted is recommending, where you're looking at a huge pattern of users and what they do with no clue as to why they're doing it, okay? So that in that situation of Sally buying the apple because her boyfriend is there, it doesn't mean that she liked apples, but generally her taste will match the pattern of other people who do similar things, and the apple is a little bit of an outlier for her, and so when you're looking at a huge system of users, it kind of falls away. So I think that in recommendation systems that aren't using this technique, I mean, the Christmas music is an issue, that you'll be more likely to have that lead you astray than in a situation where you bought a gift for somebody as opposed to a reflects your own taste, because in fact that gift is an outlier of a pattern of taste, and it just won't match what other people are doing.
But it is true that even though she now has a new boyfriend who's allergic to apples, it will still recommend them for a while. But literally,
Oh, I thought it would, that's my.
no, it would, because the gifting behavior is in her history. And until that fades into the past, it doesn't know that the physics of the world have changed. But generally what you'll also see is a difference in how people view what's right and wrong and good and bad. If Ellen holds her card up, you'll see it says scientist. If I hold my card up, it says, well, it used to say engineer. It says architect now just because that's fashionable, but it should say engineer. And so what works on a schedule is what I care about. What's true tends to be what she cares about. There's a big difference there. And you have to kind of decide what you really want. Are you looking for the truth of nature? Are you working for something that's going to work on Monday before your boss gets advantage? And I'm a pretty pragmatic guy when it comes to this. Because you shouldn't spend your life, if you're at a company that needs to make some money, shouldn't spend your life learning the nuances of every customer, unless there's only 20. And you shouldn't learn the nuances of every machine algorithm out there. You should start learning the nuances of your customers at large, your items, and how what you're recording reflects their preferences. So you need to get, speaking as a supposed expert on recommenders, you need to get the recommender stuff out of the way and start looking at the real issues of what data do you have, what data could you have. The could you have is a great example. We were recording clicks on videos, and so we started recommending spammy titles because people would click on them. We had to re-engineer the system to measure, did the person watch the first 30 seconds? Started recommending things that people would engage in, much better results. And because we had the recommender out of the way, we weren't fixated on that, we could think about what's really going wrong here, why? What are people really doing at large, not in the instance?
Thank you.
Sure. Yeah.
So question is, if I have a small inventory of product to recommend, for example, like 1,000, 2,000 product to recommend user, but I have a large user base, like does this method also apply to that problem?
So this is the inventory problem where, I mean, in the extreme, suppose you have 10 of these items and you want to sell them. Now, this begins to be a much more complicated problem because you want to allocate them to the people who will give you the most money for them. Not necessarily even the ones who want it the most. Because you've got kind of a trade-off. If I give, the people in the front row all of my items because they came first, then the guy in the third row who just will pay me enormous amounts for it, I don't get to offer it to him because I've used it up. And so it's a very, very difficult problem now to start saying, well, I won't give it to you, even though you think you appear to be a person who would like it. I'm going to hold it back so that I'll give another one. And these begin to be much, much more complex recommendation engines. Much, much more like ad targeting systems. In fact, there was a guy sitting next to you or somewhere, Dimitri, who just built a big ad targeting system that does a lot of these trade-offs in real time. Now, if you just want to sell as quickly as possible, then just recommend, and it'll work great. Now, it won't learn very long because you only had 10 of them or 1,000 of them. So what you generally have to do is start recommending characteristics of items, not the items themselves. Like red shoes. Don't recommend those to me. Ooh, I don't have them on. But you could recommend other things to me. So, look at this. See, this is my thumb drive. It's silver and shiny. So it's a thumb drive, and it's silver and shiny. You could recommend other silver shiny thumb drives when these went out of stock. And indeed, I bought other silver shiny thumb drives. And so you could make an indirect recommendation in those cases.
So along this question on the indicator,
Yeah.
like what do you recommend to set the indicator? The indicator more like a specific product or a category of products?
I always suggest that you use the actual product first, unless you have small inventory things, and then it should be a characteristic or combination of characteristics. Yeah.
So how do you judge that? Like, what is a good metric for evaluating the recommendation? How do you judge whether you need to add credit to
So-
get more data? Or...
Yeah, by the way, Dimitri just came back, so you can ask him questions about allocation. No, you, Dimitri. The question he asked about allocation recommendations, so we have a limited inventory, how do you decide? And it's a hard question, right?
Yes.
Yeah, okay. So back in the back, how do you decide what's good? And the quick answer is, does it work? Does it work well? And so you run multiple versions of the recommendation engine in parallel, and you do a parameterized Bayesian sort of test to decide which parameters make it work well.
So what is work well? Work well is a qualitative thing, right?
You remember her slide where she said, decide what good is good, what is good? What does good mean? You decide what good means to you. Now, it might mean more people give you money. It might mean more people watch your videos or listen to songs or whatever. But you might have a secondary goal as well. Maybe it means people stay on your website longer. Or it might mean people leave your website but come back. So leave it quickly but come back later. You decide what good means. I cannot. And then you measure that, and then you compare systems to see what settings, what data, what algorithms even give you better results.
I have a very quick question, as Ted's taking the last questions. If there's anybody in the room who wanted a book and didn't get one, if you put your hands up, I'll just quietly come hand you a book.
Also, if you only got one signature in your book, come up and we'll sign a second signature. Yeah, over there, Mark. Oh, you want a book? Oh, then we now have a real problem here.
Go ahead and take
Okay,
questions.
hold your hand up for the book.
Stand-
Wave your hand if you have
Hang
a
on.
question.
Just stand up. Stand up if you have a question. If you want a book, put your hand up.
Okay.
That's right.
Yeah. No, we have way lot of books.
So if
O'Reilly was
anybody
quite
had a
generous.
question, please stand up. Okay. He
Yeah,
wants a
he's-
book and
You're this way fairly simple algorithm. Explain the recommendation.
Ah, good question. So we've had four of the best questions tonight that you get on these questions. Can the recommendation engine explain the thing? Well, absolutely it can. It can say why it thinks you did it. I mean, you bought an apple. Of course you want a puppy. It can explain it at that simple level. But usually when you want an explanation, you want not really why it did what it did. Ellen, there's a hand up. I don't know if she's standing up or not.
No, I'm seeing.
Okay. So often what you will do is you'll have a catalog of acceptable answers, and you build a secondary system which will adduce what is the most salient, humanly understandable reason. So you build a recommender or a classifier or a fraud finder or whatever you do, and then you build a second model which is a reason code generator. So that's almost always in practice the way this is done. Nobody wants interpretability in the model that's making the decision. They absolutely want the best performance. And then they want some good interpretation, usually for kind of cynical reasons. Either just to explain it so that there's a UI sort of thing, so that people go, I get it. Or to get regulators, to believe you or something like that. And so a secondary reason code is usually the best answer there.
So to follow up, I was wondering whether if you could give the people a reason and say, was this a good reason or not? Does that turn out to be good information to feedback and recommend?
Is marking the reason as a good reason or not?
Like thumbs up or thumbs down. Hey,
Yeah.
we recommended this to you, here's why.
One thing that you can do there is you can let people edit their history, either directly or indirectly. And if they start saying that's a bad reason or something, you might start saying, well, maybe I'll just pull that out of your history. But yeah, you can kind of do a reverse recommendation to figure out what are plausible things to say there. And yeah, that's a good idea, actually. Negatives are very hard to deal with in general. When people say, no, this is a bad recommendation, people don't care about things that are very bad recommendations. They're far away from what they want. They utterly hate things that are quite close to good recommendations. And they love the things that are almost identical to the things that they hate. But they don't care about things that are far away. And I stepped in this big time once. I said to somebody, I said, boy, this recommendation is kind of weird because it recommended this set of stuff to these people and that set to the other. I think we have a bug. And the person just exploded. He said, no, that's black metal and this is death metal. They are not the same. And I'm going blank, blank, blank. It's like, I have no idea. I just had no idea. I could not tell the difference. I mean, one of them sang Norse sagas to guitar heavy metal accompaniment, and that was apparently death metal. And then these guys over here were black metal, and I just couldn't tell. I mean, it was bizarre. And so out of context, out of the specialized knowledge where you care, you just can't understand what they're saying. And so letting people edit their preferences, pushing things back into the recommendation engine is exceedingly dangerous. Letting them edit their history is probably not so dangerous.
I should have said this earlier, but first of all, and correct me, Pasha, if I'm correct or incorrect, but I think that O'Reilly donated the first 50 books, and we say thank you to O'Reilly, and MapR Technologies donated the rest of them. So.
The hat doesn't match the book because the book is red. The hat matches the book because of total coincidence. They're red books because they're from O'Reilly. Yeah. Any other questions? Yeah.
So this is a little bit out. Do you know what is the current status in the industry of application of emotional-based recommendation and social influence-based recommendation? These are academic topics. But is there anybody that is working on these things in the industry?
Did you say emotional-based?
Emotional-based. So for example, if you're angry or upset, you're going to do something that is different that you do when you're in a normal status.
And then there's social-based.
Social-based is, if I'm your friend, you're going to listen to me more than somebody else.
Yeah.
So I'm going to affect your decision behavior much more than other ones. So
yeah.
There is research in academia in this direction, and there are recommendations that are much more performing than what, at least on the academic papers. I wonder if anybody in the industry is doing anything.
Yes, people are. So, but mostly indirectly. As far as the emotional-based things, people use the words, so in academia, if you're doing a study with subjects, they're there in front of you. You could stick a galvanic skin response thing on them. Can't do that on the web. So we have to observe something indirectly. So we can observe words that they say, clicks that they make, scrolls that they do or do not. And what happens there is the system will pick up on those cues quite strongly, if they're strong cues. But that's very hard to say that that's any different from any multimodal recommendation engine. Multimodal recommendations engines are much better than unimodal. And one of the modes that it can be using, one of the modes of input, are indicators of emotion, like what comments do people make, or what do they say, and so on. And so, yes, they do that, but they do it indirectly by a general mechanism. Social recommendation, I have to say that I've been out of building recommenders myself for a couple of years, and over those last 3 to 5 years is when social networks have really become high enough quality to matter, I think. But it's been well established since the late 90s, I think, mid to late 90s, that most of, for instance, most of musical listening behavior is in fact social. People think that they like music because they like it and because it's good, but in fact, 60 to 80% of their decision information theoretically is based on social characteristics, like friends recommending, or even pseudo-friends. You know, these were random numbers that were on the display when the tests were done. Most of what people decided is social. And for older people who liked Bob Dylan, that the test is, would you like music that sounds like Bob Dylan? I think not, because it sounds like crap. But there's social reasons that you might like it. And then this is true of modern music and all the music in between. The stuff that's popular is pop stuff that you imprinted on at a certain social phase in your life. And so it's very clear that that has a huge impact. But I don't know of people who have already applied it well. I mean, you could put a little circle and distant and close sort of things, but I don't know of any good work on that in the industry. Yeah.
Take maybe the last question.
You guys are gonna have to fight over it.
Yeah, staying on that topic of social, so for online social networks, the whole concept of relevance and discovery, people I should know or get to know. Is anybody in the industry tackling that? So, for example, is so-and-so has X number of followers, so they're influential, or they tweet about such and such topic, so that makes them an expert in that domain space.
Yeah, I mean, people are all over.
How you might address that. Okay.
People are all over the problems of social. Who do you know and why do you know? Who should you know? Who should I introduce? Who are you following? Who actually is influential? Who just has 10,000 spam followers? Things like that. People are all over those kind of problems. And by the way, back to the social question, it occurs to me that the multimodal thing, I have 30 seconds to think now, is really good here because as a history, you can use your behavior, but you can also use your friend's behavior as a history input. So it can be multimodal in a second sense where you have two behavior vectors and you can recommend off of both of those. And that will give you the social recommendation out of these simple techniques very easily. And then the Bayesian evaluation can put a good weight on how much of that you should look at. So I think that's pretty straightforward to do. And the other one about who do you know, who's influential, there's just a vat of people that I've talked to who are doing some form of that. And I've imagine you guys have talked even more. Well, thank you again. And thanks again. Like I said, this is very good.
Go to the Hive data website. Ellen posted a blog this morning, is it, or yesterday? And so on the same topic, follow us on Twitter, and if you'd like to chat some more with Ted, stick around. Thank you for the great conversation, and thank you both for such a great evening.
Everything was very short. This sounds like something. Later
Yeah, that's
anyway, so it's good. You got something.
But if you want to know more about and embedded in there, you can kind of figure out where to get certain sites.
Yeah, I did. Now I see that it's a big deal, which is already makes it more difficult. Thanks for that.
See if I can.
can I borrow your pen? So you might even speak in this. That's right.
C'est bien.